Hey guys, this is FTC part 2. This is it's pretty short lesson. I'm hoping I can get this all knocked out in one video. So I'm going to try and do it relatively quickly, but really the big deal here, well, it says it right there. The big deal here is that integrals and derivatives are inverses of each other. So the derivative of an integral of a function is just a function. Like they kind of undo each other. This is the derivative part, as we recall from first semester. This is the integral part, not the a, but this symbol here is the integral part. And so a derivative of an integral of a function is just the function. And there's some extra variables going on in here. I don't want you to get too thrown off by them. But basically it's like you plug in like this variable, the t here will always match this one, and the x here will always match the thing at the end. So it looks like that. Again, you hardly have to think about that, because basically what you do is to take a derivative like this, you just plug in whatever's up here into the function. So there's an x up here, so I plug it in everywhere I see a t in this original function. That's why there's two variables, because I can't plug an x in where I see an x. Doesn't make any sense. So basically, we can evaluate this thing by it's a derivative of an integral. Ooh, I didn't say this. It's very important that down here is a number. There has to be a number down here. This a is like a number. A is a number. 0 or 10 or 50 billion or whatever. It's a number. Doesn't matter what number, but it has to be a number. So this derivative with respect to x of this integral with respect to t, all you got to do is you plug the x in where the t is. I don't know why I'm writing in green, but what the hell? X squared plus 1. You see, I just replaced the t here. Square root of t squared plus 1, I replaced it with the x. That was it. Nothing else to it. Second fundamental theorem of calculus. Seems really easy, but it gets a little trickier, but not hugely so. So again, derivative with respect to theta, and there's a theta up here, and then I got some other variable here. Again, the specific variable doesn't matter, but you plug in whatever's up here in where you see the variable in this one. This is just going to be the cotangent of theta. That's it. Cotangent of theta. You were like, you thought I was going to say something else, but I didn't. That's it. These kinds of integrals have no c's because they're definite integrals. Essentially, really, it's because like the c's kind of cancel out, or because the derivative of a constant is 0. That's maybe another way to think about it. So I'll do a little thing in class, I think, where I explain exactly how this connects to the other fundamental theorem of calculus. We'll use a specific example that we know how to do. But for now, just understand that the derivative of an integral, you just plug in the top limit into the function, and that's the answer. So it can get a little harder. This is the thing that we just saw. The derivative with respect to x of some integral like this, you just plug the x in for the t. But, and this is the harder part, if the thing up here is not just x, if it's like a function of x, we plug the function in like we just plugged the x in, but then we have to multiply by its derivative. This may seem familiar to you. I certainly hope so. This is known as the chain rule, okay? You have to use it. You have to use the chain rule here, or else it's not going to work. So like if this thing up here, and again, in your mind, you might be like, hey, we did do that here. The thing up here, we plugged it in, we multiplied by the derivative of this, which is 1. But we just didn't really notice we were doing it because anything times 1 is just itself. So this thing, the chain rule can come into play if the thing up here is not just an x or whatever the variable happens to be. So for example, here's a thing. This didn't say what to do, but let's say it says find the derivative of h. So I would say h prime of x equals the derivative of this function here. Well, I know the derivative of an integral is just a function. And I plug the x squared in where the t was. Then I got to multiply by its derivative. That's it. This is the chain rule in all its glory. So again, the derivative of an integral, the derivative of this integral is just the function inside it, evaluated at the top limit, and then multiplied by the derivative of that top limit. That is how the second fundamental theorem of calculus works. The derivative of an integral is just the function. They cancel each other out. Here's another example. The derivative of the integral from 1 to x to the fourth, with respect to x, of secant of t dt. Well, I look at this and I say the derivative of an integral is just the function inside the integral. This is known as the integrand, by the way. I might use that word again, the integrand. Evaluated at the top limit, so I put the x to the fourth where the t was, multiplied by the derivative of that limit. That's it. Plug in the top limit, multiply by its derivative. So you recognize these because you have derivatives of integrals, and that's how you know to use the second fundamental theorem. What happens when there are derivatives of integrals? So we'll do a couple more examples because why the hell not? So this one specifically tells me to find f prime of x. So that means take the derivative of this, which means take the derivative of this. I'm going to write this out just so we can see again that I'm doing this. Derivative of an integral. Use the second fundamental theorem, which means plug in the top limit, 2 minus 2x, and multiply by its derivative. In this case, that derivative is 1, so I don't have to multiply by anything, and this is the answer. Same situation here. Again, find f prime of x. That is the derivative with respect to x of this integral, which is a function, 2t dt. So I plug the 3x in here for t, so I get 2 times 3x, and then times the derivative of this thing, which is no longer 1, it's 3. And this whole thing is actually 18x. 2 times 3 is 18, times x is 18x. So that's it. Second fundamental theorem of calculus. Nailed it. Okay, same situation. Derivative with respect to x of this function, 0 to sine x of 2t dt, which is, again, the derivative of an integral is just the integrand evaluated at, I replace the t here, evaluated at that top limit, and then times the derivative of the top limit. That's like a minus sign. I don't like that. Derivative of the limit, which is cosine x. That's a little better. I want you guys to tell me in class another way to write this function. There's a formula we learned in pre-cal. 2 sine x cosine x is also known by another name, another trig function. This is a way to rewrite it. So I'll ask you guys about that in class. It's your little surprise question from this video. And this is a different way to think about this. I wanted to do one of these because this is like an AP question. And they give you a graph of a function which is called f. And they tell you that it has horizontal tangents at 2 and 5, which means that like this is a max and this is a min basically. And they say let g be the function defined by g of x is the integral of this function. Okay, it doesn't really matter if there's a t in here. F of t dt, if I graph t versus y, I would get the same exact picture. But basically, g is the integral of this function. That's what it's saying. Okay, whatever. Now what? For what values of x does the graph of g have a point of inflection? Well, I know that a point of inflection, to find those, I take the second derivative of the function, in this case g, and I see where it's equal to 0. Really, I want to know where does g double prime change signs? Like change from positive to negative. And that generally happens when it's 0. That's certainly a good place to start looking. So given all this stuff, how am I going to find g double prime? Well, let's start by finding g prime. G prime of x equals. And remember, up here I had f of x was equal to this integral function, and I took the derivative and I just got the thing inside it. I used the second fundamental theorem. So I can do the same thing here. G prime is the derivative of this function, which we just saw is equal to f of x. You just, derivative of an integral is just a function and you plug the x in for the t, f of x. Okay, g prime is f of x. Well, I think that means that g double prime must be f prime of x. And now I'm cooking here, right? This is the graph of f, and I know that where does g double prime equal 0 is the same thing as saying, now I'm saying g double prime equals 0 means that f prime equals 0 because these things are equal. So I look at my graph and I'm like, where is f prime equal to 0? And the answer is right at these two places that told me were horizontal tangents. That's where the slope of f, the slope of the tangent line to the graph of f is equal to 0. So that happens right here at x equals 2. Happens right here at x equals 5. And the answer is C. So like we can use this thing to answer questions like this. It's also maybe notable to say, is g double prime actually changing signs at these points? And the answer is yes. If g double prime is f prime, and f prime is the slope of this graph, the slope of this graph is positive over here, and then 0, and then negative. So f prime changes signs here, which means g double prime also changes signs here. It also changes signs at 2. And then from going down here, the slope of the graph between 2 and 5 is negative, which means g double prime is negative. And then the slope of the graph is 0 when x is 5, which means g double prime is 0. And then the slope of the graph is positive. So basically what's happening here is I got g double prime greater than 0 over here. That's green, so that's cool. And then I get g double prime is less than 0 in here because the slope of the graph is negative. I get g double prime is greater than 0 here because the slope of the graph is positive. So we can talk about how confusing all this is if you want to in class, but it's a little confusing. We're talking about the slope of the graph and we're saying a double prime, which is like usually not a slope. That's usually like an inflection and concavity thing, but because of the way g was defined, that's how it turned out, right? G double prime is the slope. So hope this wasn't too long. Like I said, I was trying to make it one video because that's really too long, too short for 2 videos. So look forward to seeing you guys in class. Bye.